In this video, we're going to go example curl and divergence of a vector field. So the definition of curl is if you have a three-dimensional vector field, so f of x, y, z is p of x, y, z, you could just write a p, or q of x, y, z, comma r of x, y, z, then the curl of f is the differential operator, cross product f. I think a nice way to remember this is that curl starts with C, cross product starts with C. So we'll go through this example. The curl of f, I skipped writing this step. I just wrote out what cross product is, right? You just list standard unit vectors I, j, k, and then write the differential operator here, partial with respect to x, with respect to y, with respect to z, and then I put the components of f here in the last row. Now it's just computing a standard cross product, so I times, and then here, this is not really multiplication, but think of it, this is partial derivative with respect to y of x times y times z squared, and that's just xz squared, minus partial derivative of z with respect to x cubed yz, so just x cubed y, that's written there. Then minus, and now for the j, partial derivative of x with respect, partial derivative with respect to x of xyz squared, so that's just yz squared right there, minus partial derivative of xyz with respect to z, and that's just going to be xy, that's that xy, plus k times, now we need to do partial derivative with respect to x of x cubed yz, that's 3x squared yz, minus partial derivative with respect to y of xyz, that's just xz. I guess this is fine, but especially due to this minus sign, it might be nice to write this a little differently. So all I did was wrote in the component form and switched the order of these two terms to do that minus sign right there. And the thing to really notice is that what you get in the end is a vector field. So the curl of a vector field, curl of this vector field is this vector field right here. Curl of a vector field is a vector field. We'll do the same thing. We'll compute curl for a two-dimensional vector field using the same idea. So it's still the same definition. In fact, in the next slide, I'll leave that. But what if you had just a generic two-dimensional vector field? We'll just pretend this is three-dimensional, but there's really just a p of xy, a q of xy, and then we'll just pretend that this third component is 0. To compute the curl, you set up the same thing, and I just put the generic whatever p is and whatever q is here, and just the scalar 0 in this last component. And if you compute, well, partial derivative of y with respect to 0, that's 0. Partial derivative with respect to z of q, well, there's no z in q. Q is just q of xy, so that's why you have a 0 automatically. Same deal here. This 0 is because you're differentiating 0, and then this 0 is because you're talking partial derivative with respect to z of p, which has no z's in it. And then the last component, the k component, is the only thing that has anything. So partial derivative with respect to x of q, that's there, minus partial derivative with respect to y of p, that's right there. And if you write this in component notation, you've got that. So the whole point is that the curl of a two-dimensional vector field has a 0 for the I component, a 0 for the j component, and the k component is the only thing that might or might not be 0, but here's a formula for that. And if we go back to curl of a three-dimensional vector field being 0 if and only if the vector field is conservative, well then the curl of a two-dimensional vector field is a 0 vector, or f is conservative if and only if, well, this is 0, meaning these two things have to be equal. And this was the condition seen earlier for the conservativeness of a two-dimensional vector field. The other thing to do is compute divergence. The definition is given a three-dimensional vector field, or a two-dimensional one for that matter. Divergence is take the differential operator and dot product with the vector field. Easy to remember because divergence starts with d, dot product starts with d. And we'll look at the same vector field for our example. So the divergence is, and I just wrote for this this differential operator, wrote that out, and then just copied this right here. So when we take a dot product, it's this times that. That's not really times, just think partial derivative with respect to x of xyz. So I wrote that in, partial with respect to y of the second component, partial with respect to z of this third component right there. And I just computed some partial derivatives, and of course at the end you get something like this. Now notice this is not a vector field. We're adding these things together. A dot product does not give you a vector, it gives you a scalar. So notice that the divergence of a vector field is a scalar field, or that the divergence of a vector field is a multi-input scalar valued function.